Hello everybody, it's your friend Daniel here and welcome to another past paper video. In this video we're going to be going over GCSE Physics Higher Tier Paper 2, being the 2018 Specimen paper, which means nobody actually sat this, and it was just created by the exam board for the students and teachers to get used to the exam question style. And of course we're going to be going over the AQA paper. Now, jumping right in. Question 1, a student suspended a spring from a laboratory stand and then hung a weight from the spring, with figure 1 showing the spring before and after the weight was added. And we're asked to measure the extension of the spring shown in figure 1. Now if you draw a line across, obviously use a ruler in the actual exam, you can see that before the weight is added, it's 10 centimeters long, and after the weight is added, it's 11.3 centimeters long, which means the extension, you just minus 11.3 from 10, and you get 13 millimeters or 1.3 centimeters. Then we're given just a bit of preamble about how the student used the spring and a set of weights and a ruler to investigate how the extension of the spring depended on the weight, and they wrote the hypothesis that the extension of the spring will be directly proportional to the weight hanging from the spring, with figure 2 showing how they set up the apparatus. And then we're told before taking any measurements, the student adjusted the ruler to make it vertical. Now then, the reason it's so important that the ruler is straight and they adjust the ruler is to decrease the uncertainty, as the ruler being at an angle would make the measured extensions shorter. And then we're shown a graph of extension against weight in newtons, and we're asked what was the range of weight the students used. Now, as you can see, they didn't actually measure it when it was 0 weight. So you can't say 0 to 6 newtons, and you instead need to say 1 to 6 newtons. And why does the data plotted in figure 3 support the student's prediction? Now, the student's prediction was that it would be directly proportional. And as you may remember from maths, for something to be directly proportional, it's a straight line through the origin. And thus, because this is a straight line through the origin, it supports the student's prediction that it's directly proportional. And then we're asked to describe one technique that you could use to improve the accuracy of the measurements taken by the students. Now, there are many answers that you can use. I went for using a set square to line up the bottom of the spring with the ruler scale. Now, this is rather similar to them just adjusting it to be straight. However, with this, we're guaranteeing that it's perfectly straight, thus improving the accuracy of the measurements taken. And then we're told the student continued the investigation by increasing the range of weights added, and then we're shown a graph, and we're asked to what can we conclude from figure 4 about the deformation of the spring, and we were able to work out that the string has been plastically deformed, and that's because extension is no longer proportional to weight. The spring is undergoing plastic deformation, which means it will be permanently deformed, and when you remove the weights, it won't go back to the shape it was originally. And as I said, the reason for the conclusion is it's gone past the limit of proportionality, it's no longer a straight line, and therefore plastic deformation. And then we're given some preamble about Edwin Hubble, and we're asked to name the effect that causes galaxies moving away from Earth to have longer wavelengths, and the name of this effect is redshift, with that just being something you need to remember. And then for 2.2, from his observations, Hubble was able to calculate the speed of a galaxy and the distance of the galaxy away from the Earth. And we're given figure 5 showing the results of his calculations. And we're asked what relationship is suggested by Hubble's results. And the relationship is that the further away a galaxy is from Earth, the faster it is moving away from Earth. Now, in A level, we learned that it is pretty much directly proportional, and I think for GCSE you are expected to know it's directly proportional. But these results don't show it's directly proportional. These results just show there's a general positive correlation, so you can't talk about direct proportionality for this question. And then we're told that the observations made by Hubble support the idea that the universe is expanding, and then we're shown a figure of a balloon to mimic how the universe is expanding. And we're asked to give one strength and one weakness of the balloon model, in representing the idea of an expanding universe. And one strength is as the balloon moves apart, expands, the dots get further apart, representing the galaxies moving apart. And the one weakness of it is there's a limit to how far the balloon can expand before it pops, and we don't know what's going to happen is if the universe is going to continually expand, if it's going to start shrinking again, if the universe is going to pop even. Hopefully it doesn't. Now moving on to the next question, we're given some more preamble. Theory 1, the universe has always existed, it is continually expanding. New galaxies form as older galaxies die out. And Theory 2, the universe began from a very small region that was extremely hot and dense. The universe has been expanding ever since. And then for question 2.4, we're asked in what way did the observations made by Hubble support both Theory 1 and Theory 2? And the observations made by Hubble support both theories, as both theories suggest the universe is expanding. And then for 2.5, we're asked how most scientists now believe that Theory 2 is correct. Suggest what is likely to have caused scientists to start thinking Theory 1 is wrong. And this is due to there being new observations and evidence that cannot be explained by Theory 1, such as cosmic microwave background radiation caused by the Big Bang, which scientists are able to detect, and they would not be able to detect if the universe has always existed. Now for question 3. A student investigates how the magnification produced by a convex lens varies with distance d between the object and the lens. The student used the apparatus shown in figure 7, with that being a ray box, a convex lens, and a sharp image. Then we're told the student measured the magnification produced by the lens by measuring the image height in centimeters. And why is the image height in centimeters the same as the magnification? Now this is due to the object slit being 1 centimeter tall. And because magnification is image height over object height, and the object height is 1, and anything divided by itself by 1 is itself, so magnification is the same as object height. And you need to pay attention because it clearly says in centimeters. And anyway, moving on. The data recorded by the student is given in table 1. It would be difficult to obtain accurate magnification values for distances greater than 60 centimeters. Suggests one change that could be made so that accurate magnification values could be obtained for distances greater than 60 centimeters. And this is either using a larger or taller object. And that's so it's more visible. Anyways, moving on. We're then asked to complete the graph by plotting the missing data. I've just plotted all the points. Obviously, in an exam, draw the straight line better. And then we're asked how many times bigger is the image when the object is 35 centimeters away from the lens compared to when it's 55 centimeters away from the lens. So we take the readings for 35 and 55, and we get that the magnifications are 1.4 and 0.6. So to work out how many times bigger it is when it's 35 than when it is 55 centimeters, we simply do 1.4 over 0.6 and get 2.33 times bigger. Now moving on to 3.5. During the investigation, the students also measured the distance between the lens and the image, and table 2 gives both the distances measured and the magnification, and we're asked to consider the data in table 2 and use it to answer how a second way that the student could determine the magnification of the object, and we're asked to justify our answer with a calculation. Now this may just be something you may have been taught, however you may remember that the distance between the lens and the image over the distance between the lens and the object is equal to magnification. And I've written that here by dividing the distance between the lens and the image by the distance between the lens and the object, you get the magnification. And I've given an example, 100 over 25 equals 4. Moving on to 3.6, we're asked to complete the ray diagram. However, this is a convex lens, which means you would expect a virtual image. However, the object is closer to the lens than the focal length. So you can see if you draw the lines how you're supposed to, like going through going across and then through the focal point and just going through the center, they'll never meet on this side. So what you need to do is you need to draw back and work out where they meet here. Now, I probably should have done the imaginary lines in dotted. However, I still get the marks for that, and you can see that the images meet above the focal point, above the focal lens here. And then we're asked for question 4, figure 10 shows a straight wire passing through a piece of card. A current is passing through the wire. Describe how you could show a magnetic field has been produced around the wire. Now, there's two ways to do it. With the card, they're kind of hinting towards the fact that you use iron filings and sort of tap it until you can see the magnetic field lines. However, you could just move a compass around the wire and show how the change in direction of the compass needle shows a magnetic field has been produced by the wire. Now for 4.2, we're asked to explain this little ignition switch, and I've done a couple of drawings that I'll explain as I go through it. Now, closing the ignition switch causes a current to pass through the electromagnet, causing the iron core of the electromagnet to become magnetized. Then the electromagnet attracts the short side of the iron arm, as shown here with the little iron arm arrow going down. And then the long side of the iron arm sort of pushes the starter motor contacts together and since the starter motor circuit is now complete, a current flows through the starter motor, allowing it to turn on. So basically, the magnet activates, that goes in, the pivot forces that to go out and causes the starter motor to turn on. Moving on to question 5. The data given in table 3 was obtained from an investigation into the refraction of light at a glass boundary, and were given the angle of incidence and the angle of refraction. And when we're asked to describe an investigation a student could complete in order to obtain similar data to that given in table 3. Your answer should consider any cause of inaccuracy in the data, and the label diagram may be drawn as part of your answer. I don't think I did draw a label diagram, no, I didn't, but you could explain this stuff through a label diagram in order to pick up marks without actually having to explain it. Anyway, I've sort of written out steps here. Place a glass block on a piece of paper, draw around the glass block and then remove the glass block from the paper. Draw a line at 90 degrees to one side of the block, also known as the normal. Use a protractor to measure, and then draw a line at an angle of 20 degrees to the normal. And then you replace the glass block, put it back where it was before, and then use an array box and slit point. Using an array box and slit, point the ray of light down the drawn line and mark the ray of light emerging from the box. And then you remove the box and draw in the refracted ray, and then you measure the angle of refraction with a protractor, and then you repeat the procedure for a range of values of the angle of incidence, as you can see that they've done here. And that's all you need to write to get the full 6 marks. You could draw a labeled diagram, but it's not mandatory. 5.2, state the reason why light is refracted as it crosses from air into glass. And light refracts going from air into glass as the speed of light in the glass decreases. Now, you may have been taught that the speed of light is 3 times 10 to the 8, which is true. That's technically in a vacuum, with it barely changing in air. However, as light goes through different objects, there's a thing called a refractive index, which you may know about, that causes the speed of light to change. And the speed of light changing, if the light is not going directly through the normal, it causes the light to change direction. Question 6, we're shown the construction of a transformer, and we're asked why iron is a suitable material for the core of a transformer. And that's because it is easily magnetized. A metal which is not easily magnetized would not be suitable. And then we're asked, well, firstly we're shown for 3 different transformers, the potential difference in the primary coil to the potential difference in the secondary coil. And we're asked how we can show that transformer J is a step-down transformer. And how we can show that is that the potential difference across the secondary coil is lower than the potential difference across the primary coil, which I just wrote there. And then for 6.3, we're told that each of the transformers has 50 turns on the primary coil. Calculate the amount of turns on the secondary coil of transformer L, and we're asked to use the correct equation from the physics equation sheet. Now, secondary voltage over primary voltage is equal to the secondary turns over primary turns. Now, for transformer L, we can see that the primary voltage, secondary voltage is 12 and the primary voltage is 6. You could use any point along that line, 8 and 4, but I just decided to use 12 and 6. And 12 and 6 is equal to the secondary turns over the amount of primary turns, which is 50. So 2 is equal to secondary turns over 50. You do some simple rearranging, and then you get the number of turns on the secondary coil is 100 turns. Basically, the scientists said that a neutrino had the ability to travel faster than the speed of light, and 7.1 is to suggest why most other scientists thought the experimental results were unbelievable. And this is due to the theory that nothing can travel faster than light is supported by many other experiments. Many of you may know that the speed of light is sort of called like the universal speed limit. Nothing can go faster than it. And the neutrino results disproved that, although this was due to a mistake, as the later questions will show. And for 7.2, suggests 2 reasons why the scientists decided to publish the results, despite them not being able to explain it. And this was to allow the peer review of data and to encourage other scientists to develop experiments. Then for 7.3, the experiments conducted by the scientists involved measuring the time it took neutrinos to travel from CERN to another laboratory 730,000 meters away. Using the data, the speed of the neutrinos was calculated to be 300,000 million 7,400. Calculate the time it would take the neutrinos to travel 730,000 meters at a speed of 300,007,400 meters per second, and give your answer in standard form. Now what we need to do for this is we just need to do distance equals speed times time, and then do some simple rearranging to get time equals 730,000 over 300,007,400 equals 2.43 times 10 to the power of minus 3. Now, next question, which of the following is the same as 60 nanoseconds? Now, you could just remember this, or that nano is times 10 to the minus 9, or you can remember this helpful little acronym I have here. Terry's gun malfunction killing multiple Mews. No. And what this is the blank space represents just no prefix, and each time you go up, you times it by 10 to the 3, and each time you go down, you times it by 10 to the minus 3, of course, including the magical space. Now, this may seem a bit silly, but the sillier a mnemonic is, the better it is. And the reason I went for Mews here is because the symbol for micro is the Greek symbol mu. And then we're talking about the error. It's always 60 nanoseconds less than the actual time. What name is given to the type of error made by scientists? And that's a systematic error, with a systematic error always being an error that's off by a specific period of time, while a random error, the time it's off by varies. Now, I suggest what a scientist could do to calculate an accurate value. Well, if it's always 60 nanoseconds less than it should be, you can just add on the 60 nanoseconds and recalculate the speed. Moving on to question 8. Figure 14 shows the route taken by the train. Figure 14 has been drawn to scale. 8.1, the distance the train travels between A and B is not the same as the displacement of the train. What is the distance between distance and displacement? Distance has magnitude only, while displacement has magnitude and vector. So as you can see, the distance the train travels is along the route. However, the displacement is from the beginning point to the end point, so the displacement is actually less than the distance. And then we're asked to measure the displacement, including an angle. and the distance. Now, what we can see is the scale is 1 centimeter represents 5 kilometers. Obviously, this is online. Can't actually use a ruler, but the distance between town A and town B is 7.5 centimeters. Times that by 5, you get the amount of kilometers, which is 37.5. And then displacement, because you have it because you have the north measurement, you can give the direction as a bearing, and the bearing is 62 degrees from north. Now for 8.3, there are places on the journey where the train accelerates without changing speed. As you can see, in multiple places, the train changes direction, which means the train changes its velocity. However, and because acceleration is the rate of change of velocity, the train change in velocity causes the train to accelerate. However, because the train is still going at a constant speed, it can undergo acceleration while maintaining a constant speed. Now moving on to 8.4, we're showing how the velocity of the train changes with time as the train travels along the straight section of the journey. As you can see, I've counted the squares. And estimate the distance travelled by the train along the section of the journey. To gain full marks, you must show how you worked out your answer. Well, distance is speed times time. Therefore, distance is equal to the area under the graph. And you can work out the distance that each square is equal to by timesing the time and the speed. So then you get the distance of 500 meters per square, and then you just count the amount of squares. I've done a couple of bundling here. I probably could have bundled these better, like bundling one of the 15s with one of the 16s and so forth. But this general thing shows that there are like approximately 17 squares, which means that you simply times 17 by the distance for each square. 17 times 500, 8,500. The distance is 8,500 meters. Now, for question 9, we're shown the stopping distance and how the speed affects the thinking distance and braking distance. And we're asked what is meant by the braking distance of a vehicle. And that is the distance travelled after the brake/braking force is applied. Now for 9.2, the figure in table 4 refers to a car in good mechanical condition driven by an alert driver. Explain why the stopping distance of the car increases if the driver is tired. And this is due to their reaction time will increase, leading to an increased fixing distance and thus increasing the stopping distance. Now you need to be a bit careful here. Their reaction time increasing is a bad thing. It will cause them to take longer to react. And it can be a bit like finicky, because their reaction time will increase, therefore it will be better and they'll react quicker. And that's simply just confusing reaction time and reaction speed, and you need to be careful not to do that. I've had a lot of students who have made that mistake, and it does cost them the mark, because the mark scheme is very specific on reaction time will increase. Then the student looks at the data in table 4 and writes the following. Explain whether the student is correct. And they're not correct, because when the speed increases, the thinking distance increases by the same factor. The braking distance does not. For example, increasing from 10 meters per second to 20 meters per second increases the thinking distance from 6 to 12 meters, but the braking distance increases by 4 times instead of doubling from 6 to 24 meters. Then we're shown a bit of preamble. Applying the brakes with too much force can cause a car to skid. Figure 16 shows a sled being pulled correctly and incorrectly across the surface. The constant of friction for the surface is calculated from the force pulling the sled and the weight of the sled. And why is it important the sled is pulled at constant speed? And if the sled accelerates, the value for the constant of friction will be wrong. Now you may not be able to work that out just from it, however the other ones will either have no effect on the experiment or just aren't true. So that's the only possible result that could be correct. Now for 9.5, if the sled is pulled at an angle to the surface, the value calculated for the constant of friction would not be appropriate. And this is due to the horizontal component of the force pulling the sled forward and the vertical component of the force lifts the sled, reducing the force of the surface on the sled. So as you can see, if you're pulling it at an angle, there's a vertical force pulling it upwards, which changes the reaction force, messing up the experiment, as you won't be able to correctly determine the reaction force. And then for 9.6, by measuring the length of the skid marks, an accident investigator determines the distance the car travelled between the brakes being applied and the stopping was 22 meters, and then they just sort of give you a bunch of things and expect you to use your formula book. So what we have is that because it stopped, the final speed was 0 meters per second, and we have the deceleration and we have the distance, and we have to use one of the Suvat equations from the A-level physics formula booklet. And what we do is v squared equals u squared plus 2as, and then we get, because v squared is 0, let me just 0 equals u squared plus 2 times minus 7.2, because it's decelerating, times 22. And then we just do some rearranging, move the u squared across, turn that into a positive. U squared equals 316.8, and u squared equals 17.8. However, because we want it to two significant figures, the speed of the car before the brakes was applied was 18 meters per second. And then for figure 17, we've shown how atmospheric pressure varies with altitude, and we're asked to explain why atmospheric pressure decreases with increasing altitude. And this is due to this is due to the definition of pressure being that it's air molecules colliding with a surface and applying force to that surface. And as altitude increases, there are fewer air molecules, meaning fewer collisions occur as altitude increases, and thus pressure decreases as altitude increases. It's a bit circular, explaining why pressure decreases with increasing altitude. It's a bit tricky for 3 marks, just to make sure you get all 3 marks, but overall it's a fairly nice question. Then for 10.2, when flying, the pressure inside the cabin of an aircraft is kept at 70 kilopascals. The aircraft window has an area of 810 centimeters squared. Use data from figure 17 to calculate the resultant force acting on the aircraft window when the aircraft is flying at an altitude of 12 kilometers. So basically, 12 kilometers above sea level, you go across, you work out the atmospheric pressure in kilopascals is 20. So the atmospheric pressure in kilopascals outside the plane is 20 kilopascals, and inside the plane it's 70. So there's a pressure difference of 50 kilopascals. And therefore, because pressure equals force over area, force equals pressure over area. So you just times the pressure, which is 50 times 10 to the power 3 because it's kilopascals. Remember, Terry's gown malfunctioned, killing multiple mews. No, to use that. And also you need to convert 810 centimeters squared into meters squared. And then you just do 0.81 times 50 times 10 to the power 3, and you get a force acting on an aircraft window to be 4,050 newtons. And because it wants it to two significant figures, you round it to 4,100 newtons. Then for figure 18, we've shown the cross-sectional area of one type of aircraft window, and we're explaining why the window has been designed to have this shape, and this is due to the force from the air pressure acting from the inside to the outside of the window is bigger than the force acting inwards, so this keeps the window in position, with the shape helping that. Like, as we can see, the force would be sort of acting in this direction because there's a higher pressure inside the cabin. However, and that sort of forces it into this like shape. However, the force was going inside into the cabin, the windows would very easily just sort of pop out. Anyway, moving on. Question 11. Waves may either be longitudinal or transversal. Describe the difference between a longitudinal and transverse wave. Now, usually I don't do this, but I've just copy and pasted it from the mark scheme here, because it's a definition you need to remember, and it's best to just go with the mark scheme definition instead of correctly creating our own. And that is, in a longitudinal wave, the oscillations are parallel to direction of energy transfer, and in the transverse wave, the oscillations/vibrations are perpendicular to the direction of energy transfer. And 11.2, describe one piece of evidence that shows when a sound wave travels through the air, it is the wave and not the air itself that travels. And this is due to the example I came up with. It's not the one they have in the mark scheme. They only have one in the mark scheme and it's not worded very well. So I came up with one that demonstrates the same property, but is better worded and is easier to understand. And that is the fact that a tuning fork can cause other things to vibrate, but doesn't actually move the air around it. For example, if you put like a tuning fork next to another tuning fork, it causes the other tuning fork to vibrate. However, the air between the two tuning forks doesn't actually move. Moving on to 11.3, figure 19 shows the part of a moving coil loudspeaker. A coil of wire is positioned in the gap between the north and south poles, and we're asked to explain how the loud signal converts current and electrical signal to a sound wave. This is a very hard question for GCSE. I've seen this in A level a couple of times, so I'm just going to go through the answer. You can learn from it. However, this is highly unlikely to come up in such depth. And if it is, grade boundaries are going to be low. Well, grade boundaries are always low for sciences. In a loudspeaker, the varying electrical current in a circuit flows through a coil placed in a magnetic field, causing the coil to experience a force whose direction depends on the direction of the current. Reversing the current reverses the direction of the force, with the size of the force increasing with the size of the current, as the current continuously changes. Right, there's meant to be a full stop. As the current continuously changes, the coil vibrates. Attached to the coil is a cone, which also vibrates as the coil does. These vibrations are transferred into the surrounding air, causing air molecules to move. This movement results in pressure variations in the air, with molecules bunching together to form compressions and spreading apart to form rarefactions, with this creating a longitudinal sound wave. Now, it's a bit complicated, but it's a really hard question, in my personal opinion. And even being able to just state a few basic principles and get a few marks is good for this level of question. Now on to the last question, question 12. Figure 20 shows a piece of apparatus called a current balance, and we're just showing it there. When the switch is closed, a part of the wire labelled X experiences a force and moves downwards. What is the name of the effect that causes wire X to move downwards? And that is the motor effect. Some students may get confused with the generator effect, but the generator effect is when the movement of a wire generates current, and the motor effect is when a current generates movement of a wire. And suggest one change you can make to the apparatus in figure 20 that would increase the size of the force that wire X experiences, and that is just increasing the current through the wire. Now I believe this is the last question. Figure 21 shows how a small weight placed on an insulating bar makes wire X go back and balance in its original position. The wire is 5 centimeters long and carries a current of 1.5 amps. The small weight causes a clockwise moment of 4.8 times 10 to the minus 4 Newton meters. Calculate the magnetic flux density where wire X is positioned. And this is simply that the moment equals force times distance. So you just do 4.8 times 10 to the minus 4 equals the force times 8 times 10 to the minus 2. And you get the force being 6 times 10 to the minus 3. And then you simply plug that into force equals magnetic flux density times current times wire length. And then you simply rearrange to get the B equals 0.08 Teslas. Now the tricky thing here is that you may get the 8 centimeters confused with the 5 centimeters. However, if you do that, you still get most marks. It is a long question, with you just needing to use a couple formulas, do a bit of rearranging, and then finally remember what the unit is. Anyway, I believe that's the end of the paper. And if you liked the video, make sure to like and subscribe, and I'll see you next time.